in a retail event featuring Jacob Zweig. Sorry if I mispronounced that.
No,
And
you
Mark,
got it.
awesome, from Strong Analytics, the co-founder and principal data scientist, and Mark Moyou who's the senior data scientist over at NVIDIA. So excited to hear from both of them today. And our agenda is full, so we're going to dive right in. We're going to be going over AI in retail, how it's used, why it's used, how you can use it in your retail or e-commerce experiences if you have those, the challenges of using that, and then the solution, vector search. Always, as the title indicates, we're interested in vector search and how that can help everybody make their AI applications easier to use. We'll go over some use cases, including image search for product recognition, e-commerce product search and recommendations, and potentially data curation. Then we'll go into deployment and productionalization of vector search pipelines and have a panel Q&A with both Mark and Jacob at the end. As always, and Greg just put this in the chat, please put your questions in the Q&A box at the bottom of your screen, not the chat box, so that they are easier for us to find and they don't get buried amongst all the other folks' questions. And you can ask questions throughout, not just during the Q&A period. And of course, you'll receive this recording and deck at the end in an email, probably later today or tomorrow. And with that, I'll pass it back over to Jacob to start us off. And thank you all for being here.
Awesome. So I guess we'll keep an eye on the Q&A. It doesn't bother me if anyone wants to chime in with a question. I'm not sure if that's everyone else's preference, but I'm certainly open to it if you have it. Although you might be muted. I don't know. We'll find out. So we're going to talk about vector search in retail today. But before we do that, I think it's good to take a step back and also talk about generally AI in retail, because vector search is a component of that. And as most of you guys are probably aware, because you're here, AI can mean a lot of different things. And when we talk about AI in retail, it encompasses a lot of techniques and technologies that kind of roll up to what we refer to as AI, using air quotes here because, yeah, there's a lot of different meanings. But generally, when we're talking about it, the technologies that we're interested in include computer vision, forecasting, optimization, things like business intelligence, understanding what's going on with your business, NLP recommender systems, and a lot more. There's a lot here, right? Like all of these are applications of machine learning that we call AI in this space, and all of which are used for a pretty wide variety of purposes. So we kind of sat down and thought through a few different examples here. These are some that we thought of. I'm sure there's more. I'm sure some of you guys are even working on some more that we aren't even aware of, which is awesome. And we would love to hear about. But a few that we kind of jotted down here: AI applications for retail, so things from inventory management. Obviously, you have to know what's going on with your inventory if you're managing inventory, especially so if you have perishable goods, for example. Image-based product recognition, so all different ways to know from imagery what kind of inventory is available, which is really useful, and we'll talk about some of those applications shortly and kind of dive in there to how that works. Dynamic customer engagement. If you're a retailer and you have customers, you are probably engaging with them, and so understanding the best way to do that, how to maximize their LTV, send the right incentives, for example, at the right time. Those kinds of things are critically important to your business and are examples of using AI for retail. Conversational support and chat. Retailers receive a huge volume of communications every day. If you're interacting with your customers, there are a lot of different ways to streamline that process and kind of make sure your operations support proper engagement, and so things like routing questions, all sorts of things like that. But generally, conversational support is important for retailers. Product search and recommendation, which we will also talk about. A huge component of any retailer's business is how to engage their customers and make recommendations, right? So whether they're on your website and they want to find the complementary product or another product that they might buy, they're hugely impactful for retailers' businesses. Demand and supply forecasting and optimization, obviously important despite there being shortages of everything and it being really tricky to forecast supply. It's something that's really critical for really any retailer here, and very similar to inventory management. Loss prevention, fraud detection, all of these kind of more on the security side, as well as data curation on kind of security side. If you have any kind of customer engagement where they're uploading images, say in reviews, you want to make sure that there's not duplicates, that there's not harmful or things that we don't want on our sites. So curating data is critically important for any kind of retailer. And a lot more. So we're going to talk today about kind of two of these that we've cherry picked because they're relevant to the topic of vector search for retail, image-based product recognition, which I'll talk about, and product search and recommendations, which Mark will be discussing a little bit more. Before we dive in there, we wanted to talk through some of the key challenges, right, of deploying any AI system. And some of these are specific to some of the challenges in retail, but many are actually just broader challenges that, like, if you're deploying any AI system, you have to face. Some are a little bit more specific to retail. And this is a sample. I think we have 4 here of probably, if you put me on the spot, I could come up with 100 challenges. There are a lot of challenges. It's not an easy thing to do. But these are some that we thought were particularly salient. So the cold start problem, if you guys have ever worked with recommender systems, you're familiar with this. But the challenge is that adding either new items or new users to your system can be quite hard because you have a lack of information around them. You don't know what they've purchased in the past. You don't know their browsing behavior. If you're adding a new item, you don't know what other people are buying that complements that item. So you have this challenge of kind of continuously updating your system with new users and new items that makes it very difficult to make accurate recommendations. Low shot enrollment is a challenge, especially so for visual-based recognition systems. We, in the space of retail, we're dealing with a huge volume of items. Any store has a fairly large volume of items, and you need to be able to identify those items with a fairly limited number of examples. The common dogma when people tend to think of AI is that, oh, we need a lot of data, right? Like we need thousands and thousands of images, millions of images to be able to recognize something. And like your standard classifiers are pretty data heavy, right? So that's not a great fit for what we're talking about here. You need to be able to recognize things in a very quick and efficient way. Fine-grained classification is another challenge that we face in retail. It's actually a subdomain of the vision research. Often comes up in the context of looking for really proximal birds, which tend to look quite similar, but also applies for products because products can look really similar, right? And we have a huge volume of products. So, for example, if you're looking for the difference between tuna in oil versus tuna in water, there's a very, very subtle difference in the way that they look. Similarly, if you look at a lot of different cereal boxes, they're going to be similar. You have special editions. You have all these different things that make this a challenge to be able to discriminate between really close-looking objects. And then finally, scaling. This is a challenge for any kind of AI system, but it's not always easy, but it's relatively easy to build a proof of concept, right? Some kind of like, let's say you build a notebook, but now you want to deploy that to be a real world system and you want to scale to millions of users every single day. You want to have robust infrastructure, scaling, monitoring. Those kinds of things are really hard, right? And so it's important to address those early on in the process if you're building out a product. And make sure that you're not kind of stuck at that POC phase with something that's not going to scale. So before we jump into some of the use cases here and some information about how we actually do solve some of these challenges and actually build some of these systems for retailers, I think it's important to kind of take a step back and talk about vector search briefly. I assume if you guys are here and interested, you probably have some sense of what a vector database is. So won't dive too deep, and probably better answered by some of the Pinecone people anyway. But generally, a vector database stores vector embeddings, right? So it stores some vectorized data. And the key here is that we can use it for fast retrieval and similarity search. Right, we're not doing that really slow brute force search that you would approach if you were approaching this in a naive way. You might think to do. A vector database also sometimes, but not always, has capabilities like scaling, CRUD operations, metadata storage, and filtering, and some different approaches for filtering, pre-filtering, which can be really, really useful for some of the applications that we'll talk about. In general, though, so let's say you have a vector database. The process for searching against a vector database involves using an efficient approximate search here. So let's say you have some query, you're trying to find the closest neighbors for that query of interest, and there are a lot of different approaches in terms of the underlying algorithmic underpinnings of how we do that efficient search. Things like hierarchical, navigable, small world, I think I got that right, PQ, a lot of different crazy acronyms, but generally algorithmic solutions to enable fast search through the vector space to find the closest approximate vectors to what you're looking for. Obviously, the first step here is that you have to have some kind of vector embeddings, and we'll talk a little bit more about this in the context of image search and proc search as well. But there are a lot of different ways to get vector embeddings. Some from some really easy ones. Obviously, some of these are just APIs. Cohere, a great one. Hugging Face transformers, really great. OpenAI. You just kind of pass some text data to them, and you get back an embedding. Really cool. You can get help from us, for example. We do a lot of work here, and we've helped customers build embeddings for really complex spaces beyond just images, 3D things. Customer engagement, matching people to academic coaching, all sorts of things that rely on having some sort of vectorized representation of the data that you're interested in. Or you can ask your data science colleagues. Some of you guys coming from data science organizations, a lot of people will have some, hopefully, expertise there. Or Pinecone can help too. So a lot of different ways to get help in terms of how we generate these embeddings. And I'll talk a little bit more about how we do this in the image space. All right, so on to some applications of vector search for retail. I'll be talking here about image-based product recognition. So image-based product recognition is a task that is really important for retailers across a pretty wide variety of domains. And there's been a lot of businesses that have come up recently in this area, which have helped to enable customers to gather the kind of images that they can use for these types of tasks. So understanding your stock on shelf, if you're a hardware store, if you're a retailer, if you have some kind of parts and you have some kind of inventory, you can use images that are captured via a pretty wide variety of mediums, things like cell phones, on-shelf cameras, robotic platforms, overhead cameras. If you have cameras at checkout and you want to monitor for you want to enable automated checkout, all sorts of things like that require product recognition behind the scenes to be able to know what we're looking at when we're looking at, say, a shelf here. So the general gist of the problem here, let's say we take an example picture of the cereal aisle in the grocery store down the street from me, a great grocery store, and we want to know what's available. First, we extract some information from that, right? We want to know, okay, now we have this picture. We can obviously see what we're looking at here, but what is it that we're looking at? Ultimately, we want to derive, typically for groceries, something like a UPC, which is a unique identifier for the product that we're looking at. We don't have the resolution to scan barcodes, which is a really easy way to do that, but let's say we're not able to get a barcode because we're just looking at the shelf from some far distance and we want to monitor it regularly. So here comes our vector database, right? So we've taken our picture of our shelf, we've extracted the products that we want to look at, and now we're looking at this box of Cheerios, right? We have our vector database here in the middle, and what we want to do is find what is the closest match for that. So in this space, we look at it, it's really easy, right? Like you can tell that matches there, the visual features are similar, And we have some metadata about those things that are in our vector database, which allows us to derive a UPC. Really easy. Practically, it's not quite that easy. But as we discussed before, the first step to being able to do anything like this, to be able to load your vector database, to be able to search against it, is that you need to be able to generate some numerical representation of your query image. So this can be really anything. This could be, it could be a single number. That's probably not going to be effective. It can be some one-dimensional vector, which is most common, that enables us to search against it and find closest matches. But this needs to be just compressed, right? That can't be the full, well, I guess it could be the full image, but you're talking about a huge, like here we're looking at a three-dimensional, let's say like 480 by 480 by 3. That's just a lot of data. You want to compress that. So we pass it to some model, we get some vector, and now we're going to be able to search against it. But the problem is that your vector space needs to be expressive to enable the kind of search that we're talking about. So if, for example, you take that picture of Cheerios, you pass it to some model that you pulled from some random repository on GitHub that was trained on some Kaggle competition of whales or cats versus dogs, you're going to get an embedding, right? You're going to be able to extract an embedding. But the problem is you're going to get this really uninformative vector space because everything's going to kind of clump together. It's not distinct, it's not expressive, and it's not useful for search. So when you try to search against this, it's really hard to triangulate what you're looking for, and your UPC comes up blank, right? Like you're just not able to find what you're looking for. So that's not a good approach. It's a decent approach if you want to start and like do some experiments. It's fine to just take an ImageNet pre-trained model, but it's not if you're actually interested in building a product and deploying a product that enables you to do image-based product recognition. It's not a great approach. Instead, a better approach is to actually, as you might expect, train a model that's custom for the data that you are looking for, if that's buildings or three-dimensional parts or images of groceries. You want your model to be sufficiently distinct to be able to discriminate. And a really useful tool for enabling this is contrastive learning. So the idea behind contrastive learning is that there are objective functions, things like triplet loss, where you're explicitly trying to discriminate between objects and kind of group things together, such that the embedding space is a good representation of the input objects, and that they're sufficiently distinct. This is used, so triplet loss, I don't know if it was originally used in the face detection literature, but like it's commonly used there to distinguish similar looking objects. And here it's useful as well. And there's a whole variety of techniques from loss functions like triplet and contrastive loss, all the way to more complex like semi-supervised approaches, things like Suave and I never know how to pronounce this, SimClear is another approach, but those that rely more on different kind of approaches for training as well as really heavy data augmentation. Those tend to do a better job of building us distinct embeddings that really, when we look at the embedding space, then our clusters of objects are more unique, and thus the space is easier to search against. It's easier to find the objects that we're looking for. So I've recommended here a blog post. This is a super awesome and really, really detailed blog post, one of many that on this blog from Lillian Wang, who's at OpenAI, which describes a lot of approaches for contrastive learning. I strongly recommend it. But beyond just searching in the embedding space, the best product recognition systems use domain-specific information. So you can kind of throw all this stuff in a blender and search against your vector database, but there's still places where you're going to have ambiguities. And to resolve those, to go from like the long tail of like 90 to 99% accuracy, which is obviously what everyone's looking for, you can incorporate things like local features and geometries, spatial information, other contextual information. Really, in the end, it's domain knowledge, right? So you layer on this domain knowledge to refine predictions from your vector database. And that's what really the best in the space do to make these systems more accurate. So now we're armed with this really great expressive embedding model. And the cool thing here, this is a little bit of a diagram here of a full system that incorporates a vector database and the general process. So you have some application on the right. The first step is to load that vector database, right? So you take all of the data that you have, you batch transform, pass that through our embedding model, and load it into our vector database. And the interesting thing here for these products, for example, let's say we have those associated UPCs. So we have some metadata, right? So we have the image, the embedding, and some metadata associated with it. Those are going to go into our vector database. And now, in our live application, you get some picture of what looks to be one of the more disgusting products I've ever seen, Cinefuego Toast Crunch. You pass that to our embedding model, get some results, and you can see what the closest examples are. And you can now, because you're storing the metadata along with the images in your vector database, you can pull the relevant UPCs because you know what it matches to. So a lot of different approaches for building that vector database. Pinecone, we're here talking about Pinecone. HNSW, Weaviate. There's a lot of different approaches for it, some easier than others to implement. But in general, this is kind of an overall architecture diagram of how you might use an embedding database in a real application. And the cool thing here is that this enables that low-shot enrollment that we were talking about before. So even with a single example, let's say there's this new product that is a flop, but you want to identify it. Somebody sends you, for some reason, a picture of Cinefuego Toast on a skateboard. Who knows what they're doing? I don't know why. But you've enrolled a single example of that, and already you can identify it, right? So it solves one of the bigger challenges that we face and would not be solved by a standard classifier where you would say have to like retrain a model, have a single output for every product. It's just not feasible or practical in the case of what we're looking to do here. I see a question here, latitude, longitude as filter metadata. I think that's a question for you, Greg. I do think yes, you can use that. I think metadata, well, I won't answer that because I will allow Greg to. Some of the challenges, okay, we talked about before around AI and retail, so the cold start problem, right? So the system that we've described here solves that cold start problem for a lot of examples. It's easy to add new products to our database and start to match against them. There's a very low bar, right, to adding new information. Also, similarly, low shot enrollment. We can have a few examples and we can start to recognize products. What you don't want, what I just described before, is let's say you approach this problem of you have 50,000 products and you have a single output, like a standard in your like basic ImageNet example. You don't want to have a standard output for every single example, and you have to like retrain and fine tune. You have one example, you're not going to match to it. So this is a much better solution for this challenge of fine-grained classification when you're going to be continually adding things to the repertoire of products that you're looking for. As well, within fine-grained classification, I described here, it becomes easier to discriminate between some of these very similar products, especially when you layer in some of those additional logic steps, things like including local feature geometries. And then scaling. Pinecone, which we've used a lot on a number of projects, makes it really easy to deploy a vector database. It can be challenging to manage a vector database independently. So it's honestly just quite nice to be able to, in like a click and then like one API call, have a vector database you can start loading things to. Beyond that, Triton, which we use a lot at Strong, and I think Mark will be talking about a little bit more shortly, enables us to deploy models that can scale really effectively and handle the volume of data that we're talking about in real production systems that have millions of users every single day. So from there, we're going to move over to product search and recommendation, which I will hand over to Mark to dive into here.
Give me one sec. Everyone, good day. I guess, Jacob, let me see if I could go ahead and swap slides on my side.
Okay, yeah, I can do that.
Okay, hopefully everyone can see my screen, and just let me know if you could see the slideshow on your side as well.
Looks
Just
good over here.
All right, sweet. So everyone, my name is Moyou. I'm a senior data scientist in NVIDIA. I work as a solution architect on the retail team. So if you're in retail and you're working on search, feel free to reach out. And today, I'm just gonna kind of talk about what sort of options you have if you're leveraging, trying to deploy different models within search pipelines from an NVIDIA perspective, especially if you try to do things on the GPU. And good enough, you can do things on CPU as well. So I'd like to sort of begin the presentation with we're going to talk about NVIDIA Triton and some of the SDKs, but in this particular slide that you see, this is sort of a use case at Amazon for real-time search, I think we're doing, what you call it? Yeah, we're doing spell correction in this case. And what you'll sort of see throughout the presentation is taking a multi-modal approach to search in production, and that gives you a lot of flexibility. And basically, they leverage TensorRT and Triton. So when you think about deploying models, especially at scale for high throughput or very low latency applications, and you're trying to do multiple models, within the same pipeline to maintain your latency constraints, you'll want to leverage TensorRT. And all that means is you're building an inference specific engine for that target GPU. So that's like the fastest latency, smallest model that you can get, because you can pile directly down to the hardware. And you'll see this thing if you read the slides saying model analyzer. I'll touch on that later. And that's basically anytime you deploy something on a GPU, please deploy more than one model on the GPU. And this will help you, this tool that's free and open source will help you to figure out what's the best combination of models, batch sizes, et cetera, for you to deploy on the target GPU of your choice. Next, this is a use case from Naver. This is one of the, I think it's #1 search engine in South Korea. And they use a lot of deep learning in their search pipelines, as you can read here. But the main thing that benefited them, they leveraged Triton, because in Triton, you can deploy models on CPU and GPU with different types of querying structure as well. So that allowed them to optimize their particular search workflows that involved both CPUs and GPUs. So just kind of wanted to highlight those two use cases so you can see where this is actually being used in practice. So as we go through the rest of the slides, sort of the main buckets that we'll encounter. First, as I'm saying here, it's this high-level hybrid search architecture. That's just a ground, an opinion of maybe what an overall search architecture might look like, and I'll explain why I chose hybrid. Next is the actual platforms that you can leverage within your search workflows. And then lastly, I'll pull up a fairly detailed search diagram that you could kind of dive into. From a definition standpoint, I'm sure everyone here, we're at Pinecone, so probably not necessary, but I'm just going to call it out anyway. Lexical search, standard keyword search, we're all into neural search because we love Pinecone. And hybrid search is a combination of both, and I'll explain in the next slide why that is. And then lastly, learning to rank. You might have some learning to rank approach as the last sort of ranking at the end after you've fetched your initial set and done some filtering maybe. So here's a hybrid search architecture. So on the left-hand side, you're starting with whatever catalog data. And in this case, when I say signal data, that's all of the user interaction data that you have at query time, and you're getting from your users. It could be a bunch of different data from forums, et cetera, if you may be mining that to add synonyms to your index, etc. I put this box for training because there'll be models that you might train to detect things within your catalog on the indexing side. And then you're going to train some query time models. And after you train both those sets of models, you'll end up pushing those things to inference. And on the indexing side, you tend to have high throughput constraints, meaning you just need to push your entire product catalog, and through whatever models you're using at scale, just to get that index updated as quickly as possible, as frequently as possible, especially as new products come or item descriptions change, et cetera. And then on the query side, you want those models to be retraining all the time, quicker cycles, so that you can capture more trends based on the user interactions that are coming in. And then on the bottom, this is where you would have interacted with traditional, very large scale Apache Solar deployments or Elastic. And then when you think about neural search engines, you might consider Pinecone. And after you gotten some results, you typically might pass it through some ranking model. So it'll make a little more sense as we sort of move along in the presentation. So I'm going to make a case for probably why hybrid and not full neural search. And this is just at this time. This is more, I would say, my opinion, just from what I've observed in my prior work experience at outside of NVIDIA. So on the left-hand side, like lexical searches, as you can see here, it's very good at head and popular queries, the keyword matching. Why sometimes replicate that in a machine learning environment, in a machine learning frame. And I think one of the things that a lot of search teams really like is that ability to tune. And I think people have been conditioned to read an output log about why a particular document was ranked more than another. But the main challenge is as you think about getting very good personalized results for your users, the standard keyword approach does not take into consideration context, preferences, etc. And there's a lot of manipulation from a language standpoint where you're trying to describe someone's preferences in a human-based language, which may not truly identify their desired preference. And on the right-hand side, neurosearch is very good at handling that type of query ambiguity. From a misspelling standpoint, you might actively have a misspelling model that you're correcting the query and then sending that off to your search engine. In this case, if you do have some misspelled things because of the tokenization, depending on the model that you're using, it could sort of navigate over that and still land you on the correct product that you're looking for. From a context perspective, this is always important, entity recognition. And I think as you really think about preference, this is where neurosearch really shines. Eliminating zero results. Neurosearch will always give you back a result. You're not necessarily matching, like words matching each other. You're literally just saying, tell me the closest product in this space, and that's it. You're not necessarily operating on a human language perspective. Next is, I'm saying here, better user preference modeling because of some of the things Jacob shared earlier in you being able to learn a new vector space that every time you get a new set of data and you retrain, you're ultimately reshaping and reorganizing products in that space based on preferences of users. And you can incorporate multimodal sets of data. And as you think about the main reason why I'm saying it's not full neural yet, just because standard keyword search still makes a lot of money. So for folks that just fully switch to full neural and abandon the moneymaker, I think there'll be some time before that sort of happens. So I'm going to hop into the NVIDIA SDKs that would apply to you if you're in search. So from the top, you'll hear this thing called NV-tabular. So if you're doing any type of feature engineering on tabular data at scale, you'll definitely want to leverage NV-tabular. And it's a simple library that's built on an open source library called Rapids. As you see down here, and that's sort of end-to-end data science on the GPU. You might ask yourself, okay, why do I care about using it on the GPU? The GPUs have adopted the Apache Arrow format, which is a columnar format. So this data lives and sits very nicely on that when you think of it from a memory layout perspective. And all of the feature processing is significantly faster than you would achieve on CPU. TensorRT, I mentioned this before. If you're deploying any type of deep learning model, this will build a hardware-specific runtime engine. So let's say I'm deploying on a T4, I'll take that model, I'll compile it on the T4. So that's actually going down to the hardware level and optimizing that model. And what it does, it'll more or less analyze your model and decide, okay, what's the best number of kernel calls that I need to make? Do I need to actually access this memory in these particular patterns? And it almost rearranges your model to best operate on the GPU that you are deploying. NVIDIA Triton is another open source project that we use for inference here at NVIDIA and many other customers, as you've seen before, especially in search. And that allows you to deploy models both on CPU and GPU, but there are some other mechanisms around it that are very helpful for different types of search workflows. So, yes, and someone mentioned there a feature of keyword search, right? Is that sort of manual, and there's an interpretation layer too that I think I'm I'm really interested to see where neural search will live from an interpretation area. And then when your boss comes and says, hey, why is this document the 5th slot versus the 1st slot? And you have to give an answer. Sometimes it's a little trickier on the neural search side. You could just say, hey, the deep learning model decided that was the right thing to do. And lastly, huge CTR. I won't dive into this too much today, but if you are interested in recommender systems, we have an open source project called NVIDIA Merlin, and huge CTR is for very large scale training of sort of state-of-the-art deep learning recommender models. It's sort of written in C++, so it trains the fastest on NVIDIA GPUs. So if you're at scale, definitely check that out. Okay, I'm gonna maybe do some hand waving from a business impact perspective. And I think as you consider putting neural search into production and leveraging GPUs, I think you can get faster updates for all your users. So signals come in every night, you might want to retrain whatever encoder model that you're deploying, or you might have multiple sets of models that you're running. In terms of reducing time to A/B tests, that's more or less the same thing. If you get models out, you can do more A/B tests on different types of models. Neural search is very good at adaptive user preferencing, and especially if you have multiple models, there are different ways that you can control some of the results that you get. Mentioned 0 results before, and I think just staying ahead of the competition. If you are sort of working with the latest language models that encapsulate a lot of knowledge of just text and language and to some degree human preference, you can gain an advantage. From a technical standpoint, I'll get to some technical slides soon, no worry, for the technical, super technical folks in the room. When you think about aggregating your signals and processing that data for training, like the NVTabular library or Rapids. Rapids is, you can take, there's a library called cuDF. It's a GPU accelerated version of Pandas. So the code that you write is almost the same as you write the Pandas code, but the processing will occur a lot faster on the GPU. One of the main things that you'll discover in model training times is the actual data loading is a big bottleneck to model training. So we have those NVTabular in particular will load data onto for your model training a lot faster. This is a big one, reducing latency for model inference. If you are able to reduce the latency for your models, you can pack more and more models within the same pipeline. It could be multiple of the same ones on the same piece of hardware, or you can add more models to just get more intelligent search. At the end of the day, for very high throughput applications, you can definitely leverage Triton, as Jacob mentioned there before. And then as you think about scaling, and more importantly, standardizing your deployment. So you might have different team members that work in PyTorch, TensorFlow. You might find some other package, you might find a Python model that you might want to do post, let's say post filtering with, et cetera, you can leverage Triton to deploy a bunch of different types of models. So that'll become a little more clear later on. And then at NVIDIA, like there are some interesting efforts around doing embedding retrieval on GPUs because of the memory access is a lot faster. And especially for very high scale, you can get some benefits there. So we saw this diagram before. So I laid the actual SDKs in those particular buckets where you might experience or benefit from by leveraging it. And so hopefully that makes sense. This on the left-hand side, we're just doing some processing. This is training. This is more deployment. So if you do have deep learning models, you use TensorRT. There's some really good, much faster XGBoost inferencing that we have on CPU and GPU as well. And you can leverage Triton for ranking models, especially forest models, and then use CTR as well. Okay, so here's a fairly in-depth image of an overall hybrid search architecture. There's a lot. So we went from kind of bigger words on the slides to a lot. So let's kind of walk through it from the left-hand side. You have all of your data sources. This could have been your product catalog in addition to all of your signal data. And then what I'm showing up here in these two boxes, this is all of the ETL that you'll end up doing for your model training. This is oftentimes more signal data than like pure catalog. And then you might end up training some models for query time, entity recognition, dimensionality detection, phrase detection. And this sort of approach is still grounded in working on, let's say in this case, the English query or the native language query that comes in, and you're optimizing, adding synonyms, et cetera, to hopefully, you're not necessarily broadening the search space. You are always trying to reduce the search space, but refining that search space to something more aligned with what the user wants. You would deploy those models, and then this is what your query pipeline looks like. So on the right-hand side, when a query comes in, it goes through some type of head model. Type of head models typically have a keystroke latency that they have to respect. So every keystroke, I need to return a suggestion to you very quickly. That's often done with caching, but now it's cool to see maybe folks trying to apply a more deep learning approach to give me a sequence that would best fit these couple of characters that you're giving me so far. So as you follow this query, it goes through a query pipeline. You have some models deployed. You can do ensemble modeling in Triton as well. I'll talk about that coming up. That query then gets sent to a dense vector search engine. In addition, oftentimes to a regular lexical-based search engine, you get your vectors, and then you might do some re-ranking here to really personalize results. And then you do have merchandisers that try to promote different things and manage some of the results. They'll have that ability depending on how you set up your particular search. And then just to round out this bottom piece here on the left, you would have been working with some catalog data. You have some model registry. These would have been some of the models that you're working with on the indexing side. And then you push that through some embedding model, and you send those embeddings to something like Pinecone. And that's more or less what your overall hybrid search architecture could potentially look like, and where these particular SDKs can fit in. I see some questions in the chat. I'll make sure to grab those right after. So I just wanted to talk about NVIDIA Triton from an open source perspective. Here's kind of what you get out of the box. I would say the main benefit for a lot of machine learning teams that we see is really that standardization of the inference platform. So you can have a computer vision team, an NLP team, a speech team, a recommender team. They all deploy basically the same way in Triton, and any type of model that they're trying to deploy can be deployed on Triton. You have HTTP and gRPC. I'll show it on the next slide, just in a more diagram format. And the main thing to consider is you can deploy both on CPU and GPU across different types of hardware as well. What gets most interesting is from a querying perspective, ensemble models on the GPUs are very fast because we no longer need to sort of communicate out of the GPU onto the CPU to move data back and forth. It kind of stays natively on the GPU. So each process will talk to each other, and it's very fast because the memory access is often a lot faster on the GPU. And lastly, on the right-hand side, these are really some really cool features that we see teams taking advantage of, where you have concurrent model execution. What does that mean? That means you have multiple models on the same GPU. And if you deploy it something like Flask, you oftentimes might have a Flask server managing a single instance of your model, and you'll have multiple Flask instances managing each instance of that model to handle the query load coming in. But in this case, you can have a single Triton instance server, and it will manage all of the routing of those queries to the multiple instances of models on the GPU. And then dynamic batching, as you think about, GPUs like a lot of data. If you're not pushing a lot of data into the GPU, you're not getting the best bang for your buck. So in order to do that in a query time application, you end up setting like a very, very small delay. It can be milliseconds, where you just wait and you pull requests, and then you push as much requests through the GPU as possible. And that way you're able to actually get much higher throughput for some applications. Here's the same, more or less the same thing I shared before. In a diagram format, we have a Python and C++ client. If you actually want to go write your own backend, that's like the pure fastest thing that you could imagine possible in C++. You have that ability. And then all of the other features that I mentioned hold true. You can deploy in the cloud. It's available in all of the clouds as well. And we do have tools that will help you create Helm charts and stuff like that for deployment. Here's a little more detail on what I shared before. And I think as you think about your deployments for low latency, high throughput applications and those two pieces of the overall search architecture. These two particular types of querying patterns can be very beneficial. And for computer vision, there's this library called DALI that'll help you a lot with your pre-processing, making it a lot faster. So here's a slide on the forest inference library, and oftentimes a lot of folks work with forest type models. And if you look on this slide, well, on the left-hand side, all of that text is really trying to say, depending on the type of forest model that you have, we'll convert it to the tree-like format, and it can be deployed by the Triton Inference server. On the right-hand side, what I want you to pay attention to is, as you look at the batch sizes increasing, okay, if a GPU has a batch size of 1, like GPUs just don't like a little bit of data. However, you're seeing CPU XGBoost, that's a non-Triton-based CPU inference, and then we have CPU fill. So that's a library that we wrote, it's open source as well, to do forest inference on the CPU, and it's much faster than the current implementation of CPU XGBoost. So even at low amounts of queries or low amounts of volume, you can get significantly more throughput. And naturally, as you scale the very, very large data, GPUs significantly outperform that throughput requirement that you have. When you go to deploy multiple models on a GPU in Triton, you can leverage this tool called Model Analyzer, and it will basically take your model and try out a bunch of different configurations of batch sizes, number of models, et cetera, so that you don't run out of memory when you go to production, and you can maximize the utilization of your GPUs. Here's a very, very interesting blog, hot off the press. I think it came out it came out earlier this month. And if you are interested in deploying larger language models, we have a backend in Triton called the Faster Transformer backend, and that allows you to do multiple GPU model deployments, single model, multiple GPU, or multi-node deployments. So for these large models, you need multiple GPUs in order to give you that sub 150 millisecond type latency, and that's a single model. But if you have multiple models, you're often in a much smaller latency than that. So please check out this blog. It has code in it as well, and then you could kind of follow some of these links. The last two slides I kind of want to talk about as you think of using GPUs in the cloud, and from a latency perspective, or processing large fixed workloads for throughput, embeddings, et cetera, definitely consider leveraging GPUs, because while on a per unit, you might think they cost more, because they finish faster, you end up spending just less time. And so you spin up, you process your job, you spin down, you overall spend a lot less money. And then from an inference perspective, the cool thing about NVIDIA GPUs is that you can have the same hardware, be it in the cloud or wherever you are, but we're continuously improving the software. So you'll find that latency actually might drop over time with the same piece of hardware, because we're always improving some of the software and writing it oftentimes specifically to the type of processing cores on the GPU. I think this might be, that was probably the last slide. Yep, and in this case, this is just showing the performance on an A100. So I think I probably just deleted all the slides. That was that was a different slide, sorry. Okay, and let me take this questions.
Great, thank you both so much. Yeah, we can dive right into the questions. There are 4 that are, or 3, it looks like, that are in the Q&A box right now. The first is on the technical impact of using NVIDIA platforms for research. The first bullet, decrease signal aggregation over time. Can you talk about that, about the data curation process that creates the training data for model training?
Yeah, so it depends on how you are setting up your particular data processing for model training. So for instance, you might have individual events, like a single user interacts with this item at this time. You might want to aggregate on a user perspective. So what are all the products that a user sort of interacted with. Thanks for that question, Tim. I know that gentleman very well. So what's going to happen there is the grouping will happen a lot faster on the GPU. Oftentimes you might run these types of workloads in Spark, but depending on that type of aggregation that you want to do, the code is not that complicated to write, and you can write it in Python and it'll execute on the GPU a lot faster than the couple of hours that it might take you in Spark. And even if you do want to use Spark to do it, there's an open source library called Spark Rapids. So the same exact code that you've written in Spark, it'll GPU enable some of the operations. You know, like when you look at Spark, it kind of creates a plan for how it's going to optimize processing. Some of those operations are optimized on the GPU once you just add that jar file to your Spark deployment, and you can just process that data a lot faster and get that data indexed into your search engine, depending on what it is you're trying to do. So I see the next question. So the search is sequential from the embedding search and then the text search? Not necessarily. Just in that diagram, I was hoping to communicate maybe an asynchronous call. So your query comes in, you process it. If you're not processing any of that query to send to the neural search engine, you just send it. But you have this other pipeline that's going on at the same time. They both give you a grouping of results. And then you either have a ranking model, some rules, whatever it is that you're doing to boost. And that's not necessarily a machine learning thing, or you might have another machine learning model that just does the re-ranking, taking into account, let's say, more user features. So it depends on how you decide to set it up there. Link to dynamic batching. In the resources, we'll make sure to get that to you. And I think how can you handle that long search? Oftentimes, that's a post filtering depending, and I think it also depends on how you've indexed your data as well. So if you've indexed that type of lat long type of approach, yeah, that is a good question. I don't know if it's more advantageous to do pre-filtering before you hit your search engine or do the post filtering on the results that come out. Okay. I think that may have... Yeah, I'll follow up with you on that, Tim. I actually sent some of those libraries to the team, but I'll make sure to send it to you.
Okay. For those, oh, great. Are there any other questions, Mark or Jacob, that you want to dive in on that are in the Q&A box or that you've already seen?
No, I think it'll just be interesting to hear from folks, you know, what you're using for search today, what's your application. You might necessarily need to say the company, but maybe how many products are you searching over, maybe how many users, things that just help us to understand the scale and oftentimes the how in depth you might want to get into personalization. Oh,
yeah.
folks...
On that note, I'd love to understand. We talked at the beginning. There's probably more applications than we're thinking of. So I'd love to understand if people are using either generally machine learning, AI, or specifically vector search implementations for any other interesting applications that we haven't talked about today.
It's cool to see everyone. Well, we can't necessarily see you, but definitely thanks for spending the time with us today.
Thank you both so much. Again, you'll receive all of the wonderful material that was presented here, as well as ways to follow NVIDIA, Strong, Jacob, and Mark in an email tomorrow. Thank you all so much for attending. And if there are no more, I'll give a couple more minutes for folks to ask questions, and then we will be shutting this down for the day. Thank you both again so much. And just a quick plug for our next event, which is next Thursday as well. We will be having a demo from our product team of our new features, which just were released a couple of days ago. And if you haven't seen our release announcement, that'll be in the email, as well as a link to joining our next event. And here we look forward to seeing you there. Thank you all for joining us, and have a great rest of your day and rest of your week.
Excellent. Thanks, everyone.
Perfect. See you all. Bye.
Bye.